So I'll just instead mention my co-authors here, in particular Line Madsen, who is a PhD student with us and actually did a lot of the actual coding of this, what I'm going to present, and then a bachelor student who did some of the plotting in this particular case, and Esben, who you all know. Okay, so just very briefly, the outline here, I'll just motivate and come with the objectives, a little bit of theory, numerical implementation, and then move on to some of the results. Okay, so what we're looking at here is basically we want to do system design and comparisons between systems as accurately as possible. I've just listed a few up here: SkyTEM, VTEM, HEM systems, resolve type systems, for instance. But you see here also a non-airborne system, and this is actually probably what initiated this study, is that we started building some years ago a towed TEM system, ground-based. And one question that always arises when you do this is, what are the resolution capabilities of such a new system before you have it up and running? How does it compare to, say, an airborne frequency domain? How does it compare to near surface resolution of SkyTEM, and so on? And also, and that could both be at depth and shallow. So this is kind of the motivation that we want to do these comparisons. So already in 2014, and there's been several papers, but I'm just going to mention this, that Vest Christiansen published in 2014. He actually did publish sensitivity functions for these kinds of methods. He did it on half-space models to simplify things, and he also did not discuss at all system characteristics other than the physical positioning of transmitter and receiver. So basically what we're looking at here is that we want to be able to, I mean, this is just a sketch, that whatever the geometry is of a system, we would want to basically model that, and also model any waveform, any filters, basically how the system operates in reality, and not just on a theoretical base. And what we noticed, or what we started thinking about or discussing over coffee, is that we actually had a code that was capable of doing all this, because the sensitivity function is basically just some sort of derivative with respect to the model parameters, and we had code that was able to do that, and including all of this. This is our base code that we use for all of our airborne inversions in the first place. So it was basically a matter of starting the implementations. So just very briefly, the theory, what we're looking at here is what is referred to as the adjoint equation approach. And it was published by Hurt, and I think actually it's probably 98 and not 97 as stated here, but that's a technicality. But what we're looking at is that the sensitivity function can be expressed as in this case in the time domain, as a convolution between two E fields. And those two E fields are, just to lay it out here, is the first term here is basically where you have the E field from the transmitter working as a transmitter. So that's the normal way we think of a transmitter, calculated at some position in the subsurface with a distance r, or a position r here. And then the other term here is basically where we take, to get that E field back to our receiver, we do the same, but having the receiver acting as a transmitter. So if the receiver is a dipole, you'll set a dipole transmitter and do the same exercise, getting the E field here. And then as you see over here, then it's, to get the sensitivity function, it's basically a convolution between these two when we are in the time domain. This has also been published before this for doing it in the frequency domain. And in that case, it's basically, instead of a convolution, it's just the dot product that we're working with. But otherwise, it's the same, just a little bit simpler. Okay, so the implementation that we have been working with is MATLAB-based, where we call several times our base code and compute the E fields as we need. To do this, we basically set up a 3D grid in the subsurface that we want to compute the sensitivities in all these nodes, or in all of our subdomain. And in this case, what I'm going to show, it's actually a fairly rough discretization of the subsurface. So we have 40 nodes in the X direction, so in line with the system. We have 20 nodes in the Y direction because it's symmetrical, so we actually have 40, but it's the same on the right-hand side as it is on the left-hand side of the system when it's a symmetrical system flying in the X direction. And then we have 30 nodes in the Z direction. That's only 2,400 nodes. But then what we need to do is, of course, we need to do the calculation for each of our time gates. So say in the order of 30 to 50 time gates. And we need to compute it for both the E fields from the transmitter and from the receiver acting as a transmitter. And we need to do it in the two directions, X and Y, because in the 1D solution, there's only horizontal electric fields. So we don't need to bother about the Z direction. If it was a 3D case, we would need to have the EZ here as well. So basically what we do is that we call for each of these nodes, we loop over each of the nodes, calculate these E fields, and by doing that inside our code, we can assume any system characteristics. It'll sort of be inherent waveform and filters and so on, and gate times. We can, of course, decide as we wish. We can do it in both time and frequency domain, but I will say right now, not to disappoint anyone, that I tried as late as last night to complete the frequency domain calculations that are actually simpler, but I didn't manage to get it plotted correctly, so I'm not going to be able to show you that. So it'll only be time domain versions that I'll be able to show you. The convolution as such in the end is basically a numerical integration where, looking at this function, the two E fields would be the E field from the transmitter and the E field from the receiver acting as a transmitter. So not too complicated, actually. So what we get out of this is a 3D sensitivity cube where we have for each of the nodes, and we can grid that out into a regular grid, of course, in 3D, and then we can make any slices, of course, in that, or we can also do 2D integrations to show a 2D sensitivity distribution, or we can go all the way to the 1D and make another integration along another dimension, and then we're down to a 1D sensitivity distribution in whatever direction we're looking at, with depth or with spatial direction, X or Y. So these are basically the different options we have. And of course, there's a lot of decisions to be made. Once you start doing this, for instance, you need to decide whether negative or positive sensitivities they should cancel. That would be the case if you are thinking in a 1D context. But if you are in a 3D context, you wouldn't want negatives and positives to cancel because they would be equally valuable, and so on. So there's a lot of things that one can start playing with. Okay, so the systems that I will show are not sort of full systems, but I tried to pick some generic settings. So in one end, I'll have an airborne SkyTEM-like system, assuming only the low moment. So in this context, the SkyTEM dual moment system would be two systems, right? Because they would have each characteristic waveforms and filters. So I'm not going to be able to say one sensitivity for the full system, but I'll be able to say the sensitivity for one of the moment at a time. And in this case, I'll just assume a low moment setup. Flying altitudes I've set at 40 meters. Waveform, fairly quick ramp down, as quick as it can get, I guess, just to have a sort of an end member situation here. Low pass filters and gates distributed from very early on, just after the turn off, and up until about 1 millisecond. You can see the geometry over here, 40 meter altitude, receiver 2 meters above, 13 meters behind, so that's actually the system that's going to be modeled. And to back up or to compare that against, we'll go in the far other end, so a very high moment system with long waveforms. So in this case, it's again a 40 meter altitude for the VTEM. We'll have a 6 millisecond ramp up, but importantly here is that the ramp down is, compared to the SkyTEM, much longer. And we'll just see what that compares to when we look at the results. And gates here are also from not so early, but in the other end, much later. Okay, so what we'll start looking at is a few E fields, because this is basically the input to our sensitivity calculations. So what we'll be looking at is sort of the classic E field coming from the transmitter when it's actually transmitting. So this is what we are used to see as these smoke ring patterns, and I'm just showing here for actually just assuming just for a start that a SkyTEM system here is sitting on the ground. So just for comparison, before we move it up into the air, 10 microseconds, 100 microseconds, and 1 millisecond timing here. So now we take this system and moves it up into the air, and then what we'll see is that depth-wise, the extension with depth of this current system is not very different, but what we will see, and this is also what Niels showed in his 2014 paper, is that as we move the transmitter up, the current systems gets smeared laterally. I think that's okay and intuitive to understand for most. It's most evident at the early times. You do see it a little bit at the intermediate and later times, but by far not so evident as it is on the early times. You'll also notice that there is actually a sign change here in the E field. You have a little opposite directed smoke ring just in the front of this that you don't see when you are on the ground. We'll see that later when we look at the sensitivity functions. Okay, so that was SkyTEM. Now I'll put up, instead of the ground-based, I'll put up the VTEM in the same altitude. So that looks now like this. And just keep in mind that 10 microsecond gate would not exist in the VTEM. So the first gate here is actually at 63 microseconds. So it's not comparable in time to this one. And this is from the end of pulse. I should remember to say that. So from the end of the 1.5 millisecond turn off. And obviously what you can see is that, of course, the system is much more widespread for a later starting time than it is at the early time gates here. But what you will also see is that if we move down to the 100 microseconds, even though that this is a comparable time, what you see is that because the VTEM has a much longer turnoff, you actually have a deeper propagation of the current system even at the same time here. So the waveform in this case affected the width and the distribution of the current pulse as well. Maybe not surprising, but also again just good to see. Okay, so this was the current density, or the E field if you wish, just multiplied by the conductivity of the ground. But what we do now is that we compute a similar picture here with the receiver, and then we do the convolution, and then we look at the actual sensitivity function. So that is then a vertical slice in this 3D sensitivity distribution that we'll be looking at. And for VTEM, that looks like this. So now the timing is the same across. So for this particular pulse or E field for the VTEM, we have this sensitivity distribution. And what I think is important to note here is that if you look at the depth distribution, you would often think of depth of penetration or investigation depth to think about that as something that's related to the E field or how the smoke ring, how deep that has gone, diffusion depth. But actually what you'll see is that the actual sensitivity is actually much shallower than what you would think from looking at the E fields by itself. So they're actually much shallower, and of course they also go down, but they are at all times much shallower than the actual E fields where they have diffused to. And the reason is, again, just going back to this one, is that we have the E field from the transmitter, and then we have to take it back to the receiver, so to speak. So the distance to the observation point matters, and that means that if we look at this, then if we look at a contour here, anything that has the same value but is closer to the transmitter would have a larger weight in the sensitivity, and that means that everything will be pulled up closer to the surface. Yeah. Okay, so now I'll go to a crazy, well, from a very simple homogeneous half space, I'll just go to a much more complicated, in this case, 6-layer model. So we go straight from 1 to 6 layers. And this is a model that I choose because I thought I could use the same model to compare many different systems. Also a dual EM, it's a very small system on frequency domain, because you'll notice that the depth axis here is actually logarithmic. So it's sort of a model type that has the same sort of thickness you wish, if you want, on a logarithmic scale first layer being just 2 meters thick, and then they increase in thickness, and we end up here with the last layer boundary at 160 meter or so down. So it comes from this depth of investigation paper from some years back. So it was probably too complicated, but once I've sort of settled on that model, it's a little bit difficult to go back. But what you see here is then now just the first 5 layers of that model, and we look at the first gate again. So this is a SkyTEM 2.2 microseconds. So this is just right after the turn off of the ramp, and you can see that even at this very early time, the current density system, or the E fields, they have propagated well into the more than 10-15 meters here, and it's sitting in this low resistive layer, which is in this model would be this layer. It's a 10 ohm meter layer. And if you compare that again to the first gate of the VTEM, we're here at 63 microseconds, and we see obviously a much more widespread, but also note that the current system is actually caught in this low resistive layer, if you wish. If we then jump for SkyTEM, just to have comparable grounds here, also to 63 microseconds, we see that now the vertical distribution of the current systems are very similar, but just note again that, as we saw for the homogeneous half space, we still have this thing that the width of the current system is different, and mapping back, that difference will be kept if we look at the sensitivity functions, because these two are basically both central loop kind of systems, and they're flying at the same altitude. So you would see the same difference being mapped back into the sensitivity distributions. Just jumping a little bit forward in time, 300, whoa, that was a little bit quick. 320 microseconds, same pattern. Now we start to lose sort of the idea that they are different in width. And if we go just to look at the full domain, so this is SkyTEM at that time, and we look at the VTEM. So I just want to show this because now you can actually see that at this sort of intermediate time, because again the VTEM waveform is longer, it'll have propagated further down. So at the same intermediate time, VTEM, we would guess, would have deeper depth of information, because you actually see the current system flowing at this depth at this time. And again, just remember that the time here is from the end of the pulse. Okay, if we go on to 3 microseconds, assuming that the low moment on SkyTEM would measure out to 3 microseconds, that's a synthetic study here, so I can just assume that. We would have the current system flowing all the way down, and similarly for VTEM. So when we're at the very late times, again, we approach similar kind of setups, or similar kind of visual appearance. Okay, so what I'm going to show you now is horizontal slices of the sensitivity through these domains. So I'm going to show you a slice right through in this low resistive layer just above the boundary, and then I'm going to show you a slice in the next layer also towards the bottom of that layer. So that looks like this. Here we are at a time here at, again, this intermediate time, 320 microseconds, 17 meter depth, and you see that it's just confirmed that the width of the distribution is bigger for the system with the longer turn-off time. Again, it's just nice to have it confirmed, and you can see the axis here. It's about 400 meters where the system is in the center, so we have a sensitivity or a footprint at this intermediate time which is at least 400 meters. I'll show you some sum up numbers in 1D in a minute. If we jump to the next layer, I just want to show this. We'll just go back and forth a few times. The sensitivity distributions at the same time but at a deeper position is a little bit larger, but actually not that much. And to give you a visual understanding of the difference here, I'm going to show you what it looks like if we sit at a certain point. I think it's actually the previous one, and then we look at how does the sensitivity function evolve as a function of time. So this is now SkyTEM at 17 meters depth, so this depth slice, and now we see how does the sensitivity at that depth evolve over time. And I think what I want you to pay attention to here is that you see that at later times you have this big red anomaly, if you wish, or sensitivity distribution, but at early times it actually has the opposite sign. So you have negative sensitivity to the same layer where you have positive sensitivity at later times. So that means that if you put in a positive anomaly, it'll affect your data negatively. And it'll do opposite in the later times. I'm just stressing that because it's sort of a concept that you need to wrap your head around a little bit. That might be a little different, if you wish. Yeah, and just this animation runs just to 1 millisecond and then it restarts. But just at 1 millisecond, you can actually see that we are at this depth, also spanning almost this domain, which is 400 by 400 meters. Okay, so last thing is trying to wrap up, basically do the summation to 1D and use that to say something about footprint sizes. So what we can do here, and this was a task that has not probably been finally settled on the best way to do this, but what we're doing here is that you make an integration in 1D, you can do that with depth, and then this is just 3 different times, early, intermediate, and late. And we can now see what the sensitivity actually looks like as a function of depth. And if we have the maximum here and normalize that to 1, then we can set a threshold from the maximum at some number. And here I have chosen 95% sensitivity. Of course, that number is arbitrary. You can choose whatever you want, but I've chosen 95%. And we can do the same in the lateral 1D sensitivity. So this is, again, different times. But instead of depth, it's sort of in the x direction of the sensitivity distribution. And you can see this little hat-like structure which comes from the hole that we have in the sensitivity distribution in the middle. Okay, so this plot is the footprint depth for the homogeneous half space comparing VTEM in blue and SkyTEM in black. And as you can see, basically on a homogeneous half space, what matters is, 1, how deep you go matters with the last gate, and how shallow you go matters with the first gate. Not totally surprising, I would say. But if we take then the footprint width, the same overall picture appears. The curtains that you see here, I should say, they are numerical challenges. Or it's the discretization of the model that's not, that's not dense enough. So I'm guessing that the actual value will be sitting just on the top of these hills, if you like. So again, the footprint width starts at the earliest time to SkyTEM. Nothing around, say, 150, 160, 70 meters is the minimum footprint you have when you are at 40 meters depth, or 40 meters altitude with your system. And then basically, VTEM starts measuring here, and it's the same curve that you see. No, not depth, sorry, width. Did I say depth? I think I did. Whoa, whoa. Yeah, so depth, and this is width. And when we are at the late times here, say 5, 6 milliseconds, the total width of the current or of the sensitivity footprint is around 2 kilometers. For 95% of all the sensitivity. It would be the same if I had SkyTEM high moment and did the calculations at the same time. So these curves would be totally overlapping because it's basically the distance to the end of your ramp that matters here when you are at the very late times. Okay, so in this case, for the homogeneous half space, they're on top of each other. But as soon as we start with the layered models, things start moving a little bit, because what we have here now is that the currents will be trapped in the different layers at different times because we have these different waveforms, the short turn-off versus the long turn-off. And that makes a difference because, as we saw in the current fields, they got trapped in different ways and started jumping, if you wish, to the last layer at different times. And that's actually what you see here just before 1 millisecond. You see a certain drop in the footprint depth for the SkyTEM, and this is where the maximum of the sensitivity goes from maximum of the E field actually in this case goes from the top layer and moves down into the last layer. That then maps into the sensitivity, and we see this certain jump. Yeah. And you can also see in this case that the footprint depth is very shallow. Again, if we look at the width, we see almost the same pattern, but we also have these that it sort of stays within a layer and then all of a sudden it moves and goes to another domain. Yeah. So that brings me to the conclusions. So with this, I've shown that we can compute sensitivity functions for different systems, accounting for waveform and geometry and filters and whatever you want to model. And I would say that, illustrated nicely with this little animation, the sensitivity functions are complex and there are several sign changes in both time and space. If you plot it in different directions, it gets only more complicated than this. And with a comparison just between SkyTEM and VTEM, unfortunately, the sensitivity distribution is much shallower and narrower than the current system. So the current system is, well, if you look at the current system, then you plot the sensitivity and it goes up. And also the size of the sensitivity distribution, the footprint, depends on the pulse duration. And for the layered models, we saw that the sensitivity distribution can vary significantly with the layering. And then, as just a last little pin, because I said that we actually started this because we were wanting to look at TEM, what are the pros and the cons? So this is just showing you the footprint width for a very small ground-based system. And again, the difference you have here from a small ground-based system to the airborne is, well, it's the size of the loop, but then most importantly, it's the altitude. It's the altitude of your system that brings in most of the difference that you see here. So with that, I think I have nothing more to say.